Okay, we talked in the previous lecture how when you integrate dA over a region R, what is it that you are actually calculating by doing that? You're calculating the area of that region. Okay, we talked about that in the previous lecture. If you haven't watched that, then you should go back and watch that before doing this lecture. Okay, one thing I want to point out is because R is a two-dimensional area and dA is a two-dimensional differential, then the book does something which is it puts two integral signs here. So I'm going to start doing that, okay, which is fine. Some people do that and some don't. Okay, of course you know from the previous lecture that this is integrating dx and then integrating dy, or vice versa. So when you write it that way, when you write it like this, then of course you must have two integral signs because there's two differentials. Okay? Here, there's only one differential, so it's acceptable to only write one integral sign. But the differential is a two-dimensional differential, so it is also acceptable to write two integral signs. In other words, it's up to you. I'll write two from now on because the book has it that way. Okay, now here's the question. What is it that you're calculating if you stick a function in here? So let me put here that we're not just integrating dA, but there's some function f of xy, and we're integrating that. That function would be called the integrand. So we would be integrating f of xy with respect to x, and then integrating that with respect to y. Or if f is continuous, then you can integrate with respect to y first and then x. If you wish, you'll get the same answer. But the question I have is this. The answer that you would get would represent what? That's the question. Okay, so to figure that out, let's go back to Calc 1 and look at this situation where you have a function of one variable and you're integrating that over the interval from a to b, and here is the graph of your function f. What is it that that integral is calculating? You already know. It is calculating the area under the graph of f, right? The signed area, meaning any area below the x-axis is negative. Well, if you have a function of two variables, and you're integrating over a region R, integrating the function f of xy with respect to area, that's what I say when I see dA, I say I'm integrating with respect to area. What is it that you're really calculating? Well, what you're calculating is this. Here's our region R down here that we're integrating over. Here's the graph of our function f. And what we would be calculating in that integral is, this time, we would be calculating the volume above the region R and below the surface f. I should really say the volume between the region R and the surface f, because the surface f might be below the xy plane. Okay, and this is assigned volume. Any volume below the xy plane would be negative. Okay, so that's what you're doing when you're doing a double integral of a function, is you're calculating the volume under the surface of that function. If f is continuous, then you can integrate in either order and get the same answer. So let's just practice that. Here's a problem. It says, integrate the function x squared y with respect to area over the region R, where R is bounded by y equals the square root of x and y equals x squared. Okay, let's draw that region R. When you're doing these integrals, it's very, very good to draw not one picture, but two. Draw a flat picture where you're looking down at the xy plane and draw the region R. That's what I'm going to do first. Okay, so I have the line, or not the line, the curve, y equals the square root of x. That looks like this. And the line y equals x squared, that looks like this. So here's our region R. Now, here's something that's going to be helpful for us. What I think we should do is let's put the coordinates of the 2 points where those lines cross each other. I keep saying lines, but they're curves. Okay? This point right here, that's the point 0, 0. And this point is the point 1, 1. Okay, so there's our region R that we are integrating over. Now, I'm going to do my best. It won't be great, but I'm going to do my best to draw the three-dimensional situation, okay? So that region R is going to be around here. Here's y equals the square root of x. Here's y equals x squared. So there's our region R. And then we have the function f of xy equals x squared y, or some people would say z equals x squared y. I'm not even going to try to graph that accurately. It's not something that very many people can do on a two-dimensional surface very accurately. So let's just draw a generic surface here. Let's say that is f of xy equals x squared y. Okay, and what we are going to do is calculate the volume between here and here. We're going to calculate that volume here. Okay? All right. For practice, here's what I want to do. Set up the integral in both possible ways. Calculate that in both possible ways. Get the answer twice. Okay? So when I say both possible ways, here I've written for us two options. Option 1, integrate first with respect to x and then with respect to y. Option 2, integrate first with respect to y and then with respect to x. So let's write this down. The integral of x squared y with respect to area over the region R equals. So one way to do it is to integrate x squared y with respect to x, and then integrate that integral with respect to y. That's easy to write down. The part where you have to be careful is, what are the limits of integration? That's where you have to be careful, okay? So let's do this. First, we'll find our limits of integration with respect to x. So here's how you do that. You say, for any particular y value, x goes from where to where. The way to visualize that is to draw a horizontal line segment anywhere you want across the region R. X is going from here to here. What is that x value on the right-hand side? Well, I'm sorry, I mean the left-hand side. Well, we have the equation that y equals the square root of x. So that means that x must be y squared. On the other side, we have y equals x squared, which must mean that x is the square root of y. So x is going from y squared to the square root of y. That's our limits of integration with respect to x. From y squared to the square root of y. Okay, now, I know those limits are disappearing. I'll put them back in just a second. I want to get rid of this stuff that I wrote. Okay, let me put those limits back. From y squared to the square root of y. There we go. Okay, now we're going to find the limits of integration with respect to y. Now, I know what you might be thinking. You might be thinking, oh, now we're going to do this. That's good thinking, but that's not what we're going to do. And I'll tell you the reason why. We have to do something different this time. By the way, before I erase that red line, if I did that, what would I probably write down? I would probably say y is going from x squared to the square root of x. That's probably what I would say, right? That's wrong though, but let me just show you why it's wrong. If I say y is going from x squared to the square root of x, here's the problem I run into. That outside integral is the second integral that we're doing. It is going to be the end of the problem. When we finish the outside integral, we should have an answer for the volume, which means we should have a number. How am I going to have a number if my limits of integration are variable? That's the problem. So let me go back, let me erase that stuff. For the outside integral, you do not draw a line segment across the region R. What you do instead is you say, what is the absolute lowest y value and the absolute highest y value? Our absolute lowest y value is 0. and our absolute highest y value is 1. Those are your limits on y. When we integrate with respect to y, we're going to go from 0 to 1. Okay, so what's really important, a good way to summarize that is to say the inside limits of integration should usually be variable. They might be numbers. For instance, if r is a square, then the inside limits of integration will be numbers, but usually they are variable. And the outside limits of integration will be numerical. And one other thing to say is that the variable that is inside those limits of integration on the inside integral cannot be the variable that you're integrating with respect to. It has to be the other one. So when I'm integrating with respect to x, my limits of integration has y's in it. Okay? Let's set up the other option. I want to integrate with respect to y first and then x. Okay, then my integral of x squared y dA over r would look like this. Integrate x squared y with respect to y, and then integrate that integral with respect to x. What would our limits of integration be if we did it in that order? So in that case, you would draw a vertical line segment across r. And you would say y is going from x squared to the square root of x. Then, for your limits of integration for the outside integral, you would say our least x value is 0, and our greatest x value is 1. So x goes from 0 to 1. Okay, that's how you do it. Oops. We'll do it both ways. I want you to pay attention to how it looks different. You're going to find that doing this via option 1 and option 2 is not a simple matter of switching the letters x and y. You will see that we're actually getting different results as we go, and it isn't till the last line where the answers are going to match up. Okay, so here we go. I want to point something out to you. I'm sorry. I don't mean to be stalling, but I just want to point something out to you. Think back a couple of semesters when you learned how to integrate. What if we just had something like this? Okay, I want to ask you a question. When does this integral symbol and this differential disappear? When do you stop writing them? The answer is you stop writing them when you do the integral, right? Okay, I just did the anti-differentiation. That's when I stop writing the integral symbol. That's important for something I'm about to say right here. A lot of times, when people do double integrals, they will just write something like this. I know I'm not explaining as I'm going. That's okay. We're going to come back and do this slower. I just want to show you something. Let me think for a second here. Oh, okay. I believe this is correct, but if it's not, I'll fix it when we get there. I'll check my work, but something like this, okay. And they say, okay, I just did the inside integral, and now I'm going to do the outside integral. Okay, that is patently false, what is written there. This does not equal this. And furthermore, this does not equal this. Okay, what's gone wrong here is the fact that in this first step here, they've done the inside integral, or at least they're in the process of it. They have not yet done the outside integral, which means what? Because they haven't done the outside integral yet, that means these integral symbols should not have disappeared yet. See what I'm saying? This must still be here, or what you have written is wrong. Okay? All right, now let's do this more carefully. I just did it fairly quickly, and the results I was writing down might have been a little bit incorrect, but that doesn't change the point that I was trying to make, and the point is this. We do the integral first, which means we must still write down the outer integral symbol because we haven't done that integral yet. Okay? Now, let's do the inner one. You anti-differentiate x squared y with respect to x, and we get 1/3 x cubed y. And x is going to go from y squared to the square root of y. Now plug in those limits of integration. I haven't started doing the outside integral yet, so the integral symbol is still going to be there. So is the differential at the end. Okay, plug in the square root of y for x. We get 1/3 1/3 y to the 3/2 times y, which is 1/3 y to the 5/2. Okay, that's not what I had written down a few minutes ago, so it's good that I'm being careful here. Okay, plug in y squared for x. We get, oh, there's a minus first of all. Okay, we get 1/3 y to the 6th times y, so that's 1/3 y to the 7th. Okay, now we integrate that with respect to y, and now we get 2/21 y to the 7/2 minus 1/24 y to the 8th, and y goes from 0 to 1. Plug in those limits of integration, we get 3/56 minus 0. And so our answer is 3/56. 3/56 of a cubic unit is how much volume is in there. Okay, now let's do the same integral in the other order, option 2. Pay attention to how it looks different as we go. What we write over here will not match what we have been writing over here, and I want you to compare the two as we go. You'll see that they are actually different. It's not just a simple matter of switching x and y. We're actually going to get different results as we go. They won't match up with each other until the very end. Okay, so let's do this. Continue the outer integral symbol because we're not doing that integral yet. Now, anti-differentiate x squared y with respect to y. We get 1/2 x squared y squared, where y goes from x squared to the square root of x. which is going to give us 1/2 x squared times x, so that's 1/2 x cubed, minus 1/2 x squared times x to the 4th, so that'll be 1/2 x to the 6th. Now we anti-differentiate that with respect to x, and we get 1/8 x to the 4th minus 1/14 x to the 7th. X goes from 0 to 1. That gives us 3/56 minus 0, and so our answer is 3/56. Okay, compare those two and see how they're different. Now what you'll find, sometimes you'll find that these two options are not much different difficulty-wise. You could do either one, and it's just a matter of preference. However you write it down, that's the way you do it. But sometimes you'll find that one option is very much more work than the other. One might be very hard and the other option very easy. You can even have one be more or less impossible to figure out, and the other one could be very easy. Here's an example of that. Look at this integral. Integrate cosine y squared with respect to y from x to the square root of pi, and then integrate that with respect to x from 0 to the square root of pi. So as that is written, you would find it more or less impossible to figure out. Okay? You can try it. Take my challenge and try to do it right now. And it's not going to be very long till you get stuck. Here's where you're going to get stuck. You're going to want to do a u substitution where u is put in place of y squared. That's the obvious choice, and that would be the correct choice to make. And let's just follow that through to its logical conclusion. That allows the cosine of y squared to be written as cosine of u, so that's nice. It allows us to replace this x with what? Well, u is y squared, so when y equals x, u would equal x squared. So that would be this limit of integration would become x squared. When y is the square root of pi over 2, u would equal pi over 2. So that would be this limit of integration. No problems at all. Here's where we run into the problem. Dealing with this guy. You have to replace the differential as well, don't you? Well, if u equals y squared, then du equals 2y dy. I could move that 2 to the other side by writing 1/2 du equals y dy. And the problem I run into is I have no y to pair up with the dy so that I could replace it with 1/2 du. And that's where we would run into an impasse and we would be stuck. Okay? But we're going to use some cleverness here. And what we're going to do is we're going to say, well, cosine of y squared is continuous, so why don't we just change the order of integration? Now, be careful when you do this, okay? Some of it's very simple. It's just a matter of swapping, but some of it you have to put some thought into. Okay, so when I change the order of integration, I'm not changing the integrand, so we're still going to be integrating cosine of y squared. It doesn't become cosine of x squared or anything like that. Swapping the order of integration does not change the integrand, okay? The differentials will swap. Instead of dy and then dx. We're going to do dx and then dy. Okay, but you must be careful on the limits of integration. You do not simply swap them. You don't put the 0 to the square root of pi over 2 here and the x to the square root of pi over 2 here. That violates what I explained to you earlier, that the outside integral should have limits that are numerical, not variable. So you actually need to figure out the correct limits of integration that go with this swapped order of integration. So the way to do that is to draw the region R that is being described here. Okay? Let's draw that region. Okay. Now, watch this. The y limits of integration are x to square root of pi over 2. That means I need to graph y equals x and I need to graph y equals the square root of 2 and I need to graph, okay, now let's move to the outside here, the x limits of integration. Let's graph x equals 0 and x equals the square root of pi over 2. Now, what is being blocked in by those 4 boundaries? Well, it is this triangle right here. Now, that might be obvious to you, and then again it might not, because you might be asking this question. You might be saying, well, what about this triangle here, or something like that? Well, I would say to you, for that question, I would say, well, this line right here is not a blue line. That's the x-axis. So there's no, I didn't draw a blue boundary line there, you see. Let me also explain that, though, in a more mathematical term. But the pink limits of integration up here are telling us is it's saying that x is going to go from here to here. And then inside of that, it says y goes from x to the square root of pi over 2, which means for each x value, let me just pick an x value. How about right, whoops, I didn't mean to erase. How about right here? There's an x value right there. For that x value, y is going to go from x to the square root of pi over 2. So it's going to go from y equals x to y equals the square root of pi over 2. You see that? For this x value, y is going to go from x to the square root of pi over 2. for this x value, y is going to go from x to the square root of pi over 2. You see what I'm saying? And so we would end up with that blue shaded triangle. Okay, so now I have the region R drawn correctly. Okay, now what I want to do is turn my head sideways and look at it like this. For each y value, x is going from x equals 0 to x equals y. So my limits of integration for x are from 0 to y. Here, let's write these 2 points. Let's put their coordinates here. The corners of the triangle. That one's at 0, 0. This one's at 0 square root of pi over 2. And this corner is at square root of pi over 2, comma, square root of pi over 2. So what is the absolute smallest y value? The absolute smallest y value is 0. The largest y value is square root of pi over 2. So that's how the limits of integration should be when I swap them. Okay, you see it's not just a simple swap, they actually change. You have to look at the region R and figure out the correct limits of integration for this order of integration. Okay, now let's do the integral. Keeping in mind that the reason we're doing this is because we were unable to do it this way. We couldn't do it. So let's see if we can do it this way. All right, anti-differentiate cosine of y squared with respect to x. That's very easy. You just get cosine of y squared times x. X is going from, let's put the x behind. Cosine of y squared times x, okay? X is going from 0 to y. So we're going to get cosine of y squared times y minus cosine of y squared times 0. Well, cosine of y squared times 0 is just 0, so the outcome is we're going to end up with cosine of y squared times y. Now, let's integrate that. Here, I'm going to do that u substitution that I said earlier. I'm going to replace y squared with u. You might say, yeah, but that u substitution didn't work. But this time it will, because there's a difference. Do you see the difference? It's the extra y. The one we needed before and didn't have, now we have it. Oops, sorry. I should not have copied those limits of integration, because when you do a change of variables, you change the limits of integration. Okay, so now we're going to have cosine of y squared. Cosine of u now. Okay, u is y squared, so when y is 0, u is also 0. U is y squared, so when y is the square root of pi over 2, u is pi over 2. U is y squared, so du equals 2y dy, which means that y dy is 1/2 du. There we go. Now integrate that with respect to u. We get 1/2 times the sine of u, where u goes from 0 to pi over 2. Okay, what are we going to get? 1/2 minus 0, so our answer is 1/2. And there we go. Doing that integral as written was impossible for us. Changing the order of integration made it very easy. Okay, so we did calculate this, and the answer we found is in fact 1/2. It's just that the way we calculated it was by changing the order of integration and then doing it from there. Okay, that's it for today.